Euler angles. So the set of rotation of in R3 SO3 is a manifold of dimension 3. The set of rotation of R2, so here R3, R2, the set of rotation of in R2 SO2 is of dimension, a manifold of dimension 1. So we need only one parameter here, theta, and here we need three parameters. So let's say theta x, theta y, theta z, or phi, theta, and c. So we'll see that these parameters, well-known parameterization, are the Euler angles. So if I now I only consider in R3, so I have three axes, x, y, and z. Here the rotation with respect to x, so this one will correspond to phi, one of the Euler angle. Here theta, here psi, the heading. So it means that if I have a body, so I represent here a body like this. Classically, there is a orientation like this. Here is x, here on the left y, here z, so x1, d1, y1, and here I have the frame. Let's say x0, y0, z0, and the orientation of this body can be represented by a rotation matrix. So this rotation matrix is the product of three rotation matrices, one corresponding to phi, another one to theta, another one to psi. So this rotation matrix R, which depends on phi, theta, and c, is equal to this. So the product of the three matrices. Here, of course, we recognize that the first axis does not change. Of course, it was the case here. For theta, the second axis does not change, and here the third axis does not change. And here we see some rotation matrices. Phi is called, can be called the roll, theta the pitch, and c the yaw. So they can be considered as angle, but rigorously they correspond to variation of the Euler angles that are called the bank, the elevation, and the heading. So if you want, this corresponds to angles to represent the position of an object, whereas this corresponds to variation of these angles. But often we'll consider, for simplicity or for historical reason, they will be considered as angles. Now, if I multiply these three matrices, I will obtain this one, this matrix. And this matrix is a rotation matrix, so the Euler matrix, equal to this one. Here, this one corresponds to the vector I1, so I1. Here, I1, J1, and K1 and J1. This one corresponds to A1 expressed in the frame R0. R0 is this one. This one is a vector which corresponds to J1 with respect to R0, so this one. And the last one corresponds to the vector K1 expressed in R0. To measure the Euler angles of a vehicle, for instance, to have an idea of its orientation, we may use a gyroscope. So a gyroscope is a disc spinning very fast and maintained by three gimbals. So the largest gimbal is fixed to the vehicle, and measuring the angles at the junction between two gimbals, we can collect the Euler angles of the vehicle. If the vehicle is a car, for instance, so the two extremities here and here are fixed to the car, here and here, and due to the fact that we have some degrees of freedom due to the junction here, here, and so on, where we can measure the angles here and so on, the disk does not change its orientation even if the car change its orientation, changing, for instance, its heading or its pitch and so on. So this one, the orientation of the disk is assumed to be fixed. Now we may have what we call, due to the fact that SO3 cannot be parameterized exactly without singularities by three parameters, MC, and this is why we use quaternion or rotation matrices to represent rotation. But now, if we use these Euler angles, we may have some singularities which generate, in this case, what we call a gimbal lock. So a gimbal lock. So let me explain how it works in practice. We have here the rotation matrix. The gimbal lock occurs when cos theta is equal to 0. So in this case, this is 0, this is 0, and sine theta may be either -1 or +1. We'll consider in this case that sine theta is equal to 1, but the same reasoning occurs if it is equal to -1. So here it will be 1, and here it will be -1. In this case, this if I multiply these matrices, since everywhere I have zeros except on this diagonal, then I will have some permutation of the columns, and I will get this is equal to 0 minus sine phi cos phi 0 cos phi minus sine phi, here it's plus, and here -1, 0, and 0. Okay. Now I take this one, and I can rewrite in this way: cos phi sine phi 0, 0, -1 minus sine phi cos phi 0, 0 multiplied by minus 1, 1, 1, 0 here, and 0 here. In fact, this matrix is equal to this matrix. So now, since it is multiplied on the right, I obtain directly this one from this one by changing the order of the columns. Now, so the matrix now I consider is the product of this one. So R is equal to this matrix multiplied by this one multiplied by this one. Now, due to the fact that this matrix and this one are the same, so have the same have the same shape, I can say that the product of this matrix and this matrix is equal to cos psi minus phi. So why? Because I replaced here minus here, minus minus, plus minus and minus. So I get exactly the same cos and sine at the same place with the same sign. Minus sine of psi minus phi, 0. Sine of psi minus phi, cos psi minus phi, 0, 1, 0, and 0. And of course, multiplied by minus 1, 1, 1, 0 here to get my initial Euler matrix. In this case, we can see that psi and phi play a similar role. So it means that the derivative of R with respect to psi is equal to minus derivative, partial derivative, of R with respect to phi. Equivalently, it means that in SO3, so this one is a manifold of dimension 3, I can, if I move for some singularities, so made by the cos by theta equal p divided by 2, or as I said, cos theta equals 0. So for some singularities like this, such as this one, then if I move with respect to psi or with respect to phi, I will move on the same vector space. It means that there is some direction where in SO3 where I cannot move. So imagine that my body, my car for instance, is trying to move with respect to this direction. What will happen? I will have these forbidden angles, if you want, which corresponds to a gimbal lock, and then I will the disk will not have the freedom to move, and a torque will be applied to the disk, and it will change its orientation. Assume that I have my Euler angle phi theta and psi, and also I know their derivative psi dot, theta dot, and psi dot. Now what I want to compute is the rotation vector in the absolute frame. So say in R0 for instance. Okay. So I know that omega, this vector, is equal to the inverse of the adjoint of R dot R transpose. I know also that R is equal to the product of these three matrices phi. Thus here I will I take only this one. This one is equal to the derivative of R psi R theta R phi multiplied by, so since it is transpose, I have to reverse the order, transpose R theta transpose R psi transpose. Now this one is equal to R dot psi R theta R phi plus R psi R theta dot R phi plus R psi R theta R phi dot. So now, of course, this one I have to multiply by this one, and we can see that we will have some simplification, since I know that rotation and C transpose, if I multiply them, I will obtain the identity. So it means that here it is equal to R dot psi R psi transpose plus R psi R dot theta R theta transpose R psi transpose plus R psi R theta R phi dot R phi transpose R theta transpose R psi transpose. Okay. Now this corresponds to psi. I take another color. This one corresponds to psi dot adjoint of k. This one corresponds to theta dot adjoint of j. This one corresponds to phi dot adjoint of I. So now, of course, recall that I have this one which is here, which is in a factor of everything. So it means that omega, which is here, is equal to adjoint minus 1. This one corresponds to this one. Multiply by psi dot adjoint of k plus theta dot adjoint of R psi j plus phi dot adjoint of r psi r theta I. So now, of course, I have adjoint minus 1, which will simplify with the adjoint. And I know the expression for these matrices. So I can get that first, that it is equal to psi k plus theta dot r psi j plus phi dot r psi r theta I. And since I know this, the expression of these matrices, I will obtain omega equal psi dot multiplied by 0, 0, 1 plus theta dot multiplied by minus sin psi cos psi 0, and here plus phi dot multiplied by cos theta cos psi cos theta sin psi and minus sin theta. So we can see that as it was clear in the previous expression, that the derivative appear in a linear way. So now if I replace the matrix in a matrix form, I obtain that omega is equal to a matrix multiplied by phi dot theta dot psi dot, and this matrix is cos theta, so I take this one, cos psi minus sin psi 0, 0, 1 cos theta sin psi cos psi minus sin theta 0. So this is expressed in the frame R0. So this formula is important because from the Euler angles phi theta and psi, from their derivative phi theta, we can get the rotation vector. In the same manner, if I know phi theta and psi, and if I know the rotation vector, I can compute these derivatives. We may have a problem if this matrix is singular. So let us compute the condition where the determinant of this matrix is equal to 0. It is equal to 0, so since I have 1 here, this determinant is equal to 0 if the determinant of this 2, 2 matrix is equal to 0. It means that cos theta times cos square psi plus sine square psi equal to 0. This is equal to 1, so it means it is equivalent to cos theta equals 0, which is equivalent to theta equal plus or minus p divided by 2, and this corresponds to the gimbal lock.